Welcome, engineering students, to this visual tutorial on implementing real-time systems. Today, we are totally bridging the gap between theoretical physics and high-performance embedded software. We're going to break down the architecture of a 3D traction control system that was developed entirely in C++ using Visual Studio. You see, our goal as engineers isn't just to write code. It's about creating robust, real-time control systems that can literally interpret a chaotic physical environment and react with absolute precision. We're taking a really close look at Waqas Javaid's project to understand exactly how embedded software techniques, control engineering, and 3D simulation tools all mesh together to save lives out on the road.
But hey, before we even look at a single line of code, let's frame the actual engineering problem we're solving. Imagine you're driving down a highway and suddenly you hit a patch of black ice. A human driver needs about 3/4 of a second just to realize what even happened. By the time your foot even twitches toward that brake pedal, the car is already spinning out of control. So how do we solve this incredibly dangerous problem of traction loss using software before human awareness even kicks in? Well, the answer lies in replacing human reaction time with continuous, real-time software calculations.
Okay, let's dive into this. Here is our technical roadmap for transforming raw physics into a working C++ system today. First, we'll look at the physics of the 3D model. Second, the dynamic feedback loop. Third, the strict engineering lifecycle. And finally, the OpenGL real-time visualization.
Let's transition right into phase one, the physics of the 3D model, where we ground our simulation.
As automotive engineers, these specific parameters are the absolute foundation of our mathematical model. You simply can't control what you can't quantify, right? To simulate authentic vehicle behavior, your C++ algorithms have to constantly calculate forces like gravity, drag, and most importantly, friction. You've got to factor in the car's weight distribution, its exact center of gravity, and the wheelbase. Honestly, if these physical variables are even slightly off in your base model, the entire traction control system is going to fail when it's applied to the real world. Now, what's really interesting here is how the system has to dynamically adapt its equations based on wildly different surface conditions. A road isn't just a static object, it's a constantly changing variable. When your virtual car hits wet asphalt, the algorithm has to instantly recognize that high slip risk. If it hits snow or ice, it must calculate for extremely low grip and prepare for a massive need for correction. And gravel or sand, those introduce super unpredictable dynamics. Your software literally has to recalculate the optimal engine output and braking force for every specific surface in real time with zero lag.
And as the project's creator, Waqas Javaid notes, this is strictly a physics-based approach to simulate the vehicle's behavior. We are absolutely not just animating a car moving through a video game. We're building a rigorous, mathematically sound physical environment that reacts authentically to the control systems we're about to program.
Which brings us to phase two, the dynamic feedback loop, or as I like to call it, the digital reflex. For an engineering student, this right here is your bread and butter. The feedback control loop is the actual brain of our traction control. Think of it as a digital reflex that tames all those abstract physical concepts we just talked about. The loop is continuously monitoring the vehicle's telemetry, actively hunting for wheel slip. In the exact microsecond that physical forces cause a wheel to spin faster than the car is actually moving, the loop catches it. It then dynamically adjusts engine torque and braking force to bring back optimal traction. It's just a relentless, endless cycle of monitoring, calculating, and tweaking. To really put that into perspective, check out this comparison. We talked earlier about human reaction time being super sluggish, right? It suffers from this delayed realization of slipping. But our programmed feedback loop acts as a digital reflex. We're talking millisecond-level detection and correction. While a human driver is literally just starting to process the feeling of sliding out, the C++ program has already executed hundreds of complex calculations and corrective commands. So how do these corrective actions actually work in tandem? Well, the loop relies on two primary tricks. First, it can dynamically adjust the engine torque. If the wheels start spinning out, the system instantly throttles the engine power to those specific wheels, capping the traction force to avoid a slide. Second, it applies targeted braking force. It can physically clamp down on the spinning wheel to force it to grab the road again. By balancing these two actions perfectly within the loop, we instantly prevent the loss of grip. Let's move to phase three and see how this builds together into a real product, the strict engineering lifecycle. Because you don't just open up Visual Studio and start blindly typing, right? Developing a robust traction control system follows this exact 5-step methodological process. Step 1 is system requirements analysis, defining exactly what road surfaces the system has to handle. Step 2 is the physics-based modeling we already covered. Step 3 is algorithm development, creating the logic for surface detection and speed control. Step 4 is UI design, making an intuitive dashboard for our real-time data. And finally, Step 5, the actual C++ implementation.
And why are we writing this specifically in C++ using Visual Studio? Well, because in real-time embedded systems, performance is everything. Writing highly efficient C++ code ensures incredibly low latency and pinpoint accuracy. When you're engineering automotive control systems that dictate human safety, a delay of even a few milliseconds can be completely disastrous. Low latency is absolutely non-negotiable. C++ gives us the direct memory management and the raw processing speed we need to run our complex feedback loops flawlessly.
All right, moving into phase 4, OpenGL real-time visualization, where we finally get to see the math in action. This brilliantly illustrates how we translate invisible physics and raw C++ code into a visible, interactive environment. By integrating powerful graphics libraries like OpenGL and DirectX right into our C++ setup, we achieve real-time rendering of the car's dynamics. We get dynamic 3D environments with skies and distinct road conditions like wet asphalt or gravel. Plus, we hook up interactive keyboard controls, so this isn't just a pre-rendered video. Users can actually drive the virtual car, intentionally throw it into a skid, and watch the control system fight to stabilize the vehicle right before their eyes. Hey, it's not all just flashy 3D graphics. The user interface is completely crucial here. As the virtual car navigates these slippery environments, the UI actively displays real-time telemetry, like speed, acceleration, and most importantly, the performance of the traction system itself. For an engineer testing the system, this isn't just for looks. It provides critical, real-time feedback on how efficiently your algorithm is managing that engine torque and those braking forces. It tells you instantly if your math holds up to the real world.
So, we've seen how integrating physics-based modeling, algorithmic feedback loops, and C++ can conquer wet asphalt and gravel right here on Earth. But as engineers, your job is always to push the boundaries. So I'm going to leave you with this final thought. If we've mastered these real-time systems for terrestrial vehicles, how must these exact same physical variables, friction, gravity, torque, adapt to navigate a billion-dollar rover safely across the unpredictable sand of Mars? The principles you've learned here today are the exact same ones used to conquer the final frontier. Something to think about the next time you sit down to write a line of code.